Hello, welcome to another module in this massive open online course. So, we are looking at various types of convex sets and their relevance to practical applications, especially in the context of wireless communications and signal processing. Let us continue our discussion by looking at yet another convex set or class of convex sets, that is the convex cone. Okay, so we want to also start looking at a convex cone or a norm cone. This is another prominent class of convex sets. And well, what is a norm cone? Well, let us consider a two-dimensional scenario. Let us consider a two-dimensional vector x1, x2, and if you consider the set of all vectors, that is the set of all vectors such that magnitude of x1 is less than or equal to x2. Okay. So, we want to look at the set of all vectors x bar such that magnitude of x1 is less than or equal to x2. Alright, and this can be represented as follows. This is your x1, this is your x2, and this line represents magnitude of x1 equals x2, or these two lines. So, this is magnitude of x1 equals x2. Okay. And if you look at this region basically represents the region magnitude of x1 is less than equal to x2, and you can see this region is a cone, and this is basically also convex. So, this is termed as a simply as a cone or also a convex cone, that is you are looking at a two-dimensional vector. It is a two-dimensional plane in which we are considering all the vectors such that magnitude of x1, that is the first coordinate, magnitude of x1 is less than or equal to x2. Okay. And this is a convex region. All right. And now we can similarly form it for, and this is also termed as a norm cone. Okay. A convex cone or a norm cone. Similarly, you can look at this for a three-dimensional scenario, that is you have x bar equals x1, x2, x3, and you consider the set of all points such that if you take the first two coordinates, that is norm of x1, x2 less than equal to x3, which basically implies that square root of x1 square plus x2 square less than equal to x3. Okay. And if you plot that, in 3 dimensions, this is your x1, x2, x3, that looks similar to the cone, the shape of a classical cone that we are all familiar with. This is the region, okay, and this is the 3D cone, the classical conical shape that we are all very familiar with. And you can clearly see that this region, if you look at the interior of this cone, this is convex, and it is also reasonably easy to show that the cone is a convex region. And in general, now you get the idea. To generalize this, we have x tilde equals, let us say we have an n plus 1 dimensional vector, of which we form the first n dimensional. So, this is your n plus 1 dimensional vector. This is your n plus 1 dimensional vector, and this is x of n plus 1. This is x of n plus 1. Okay. So, this is an n dimensional vector x bar, and this is x of n plus 1, this is an additional. So, we have a x n plus 1 dimensional vector x tilde. Now, if you consider the set S of all vectors x tilde such that norm of x bar less than or equal to x n plus 1, well, this represents an n plus 1 dimensional norm cone. This represents an n plus 1 dimensional norm cone, that is a convex region, which is the relevance to us is that this is a convex region. There is a convex region, and it is a fairly important class of convex regions. It is very interesting. It is a more sophisticated convex region. In fact, it is slightly difficult to describe a practical application of the convex cone in the context of, for instance, wireless communications or signal processing at this point, but we will note that, or I would like you to note that the convex cone in fact has very interesting and very prominent applications, which we will explore during this course. It is just that it is a little difficult to set up the problem right now. We will explore problems what are known as problems that are known as SOCP, or a second order cone programs, and these have significant application and utility. So, this is an SOCP problem, second order cone programs that have conic constraints, and these have significant utility in the context of wireless communication and signal processing. These have significant utility in wireless communication and signal processing. These are second order cone programs, especially in the context of robust signal processing, robust, similar to what we have seen previously in the context of robust, for instance, estimation or robust signal processing. One of the most prominent applications of this SOCP paradigm is in the context of robust signal processing. For instance, you can look at applications such as robust beam forming, for the same beam forming problem that we can look at in a multiple antenna wireless communication system. If you make it robust, as we have seen, robust is making it resilient to the channel estimation errors, it becomes a robust beam forming problem, and all such applications can be formulated using the second order cone program SOCP, which basically involves conic sets. Alright, and we will look at them. In fact, we will look at these kind of problems in quite some detail as we proceed through the later modules or in the later stages of this course. Okay. So, now let us move on to other interesting convex sets which also arise very frequently, and these are termed as polyhedra. Now, polyhedra are basically formed from the intersection of hyperplanes and half spaces. these are formed from the intersection of hyperplanes and half spaces. For instance, in fact a finite intersection, we can note that it is a subtle point, but these are finite, formed by a finite intersection of hyperplanes and half spaces. So, for instance, we have seen that the half spaces can be represented as follows: A1 bar transpose x bar less than equal to B1, A2 bar transpose x bar less than equal to B2, so on. An bar transpose x bar less than equal to Bn. This is a collection of, this is an intersection, let us put it this way, this is an intersection of half spaces, correct. This is an intersection of half spaces. I can write this as follows. I can put all these, concatenate this in a matrix, and I can write this as A1 bar, A2 bar transpose, An bar transpose times x bar. Let me write the right hand side, B1, B2 up to Bn, and what I can use here is what is known as a component wise inequality, which means that A1 bar transpose x bar less than B1, that is each component on the left is less than each component on the right. So, this is known as a component wise inequality. Okay. This is known as a component wise inequality. It means each component, that is, we take two vectors, vector A, vector let us say u bar less than v bar, which means each component of vector u bar is less than or equal to each component of this vector v bar. Okay. So, now denoting this by the matrix A and this by the matrix B bar, I can represent this intersection of half spaces as A x bar less than or equal to B bar. Okay. So, this basically represents an intersection of half spaces. Now, similarly, remember this is an intersection of half spaces. Now, similarly, remember I can also formulate the hyperplanes as follows, that is your C1 bar transpose x bar equals D1, C2 bar transpose x bar equal D2, Cn bar transpose x bar equals Dm. Let us put this, make this as M. This is a collection of intersection of, remember each represents a hyperplane, this is an intersection of M hyperplanes. Okay. So, this is an intersection of M hyperplanes. Again I can concatenate this system, I can represent this as follows: C1 bar transpose C2 bar transpose Cm bar transpose times x bar equals B1, B2 up to Bn. So, we have C, this is the matrix C, this is the matrix, okay, let me call this as D, yeah, this is D1, D2, in fact as mentioned above, this is D1, D2, Dm. So, we have C into x bar equals D bar, this is your intersection of hyperplanes. Okay. It is a compact way of representing an intersection of hyperplanes. And now if you put them together, you have an intersection of hyperplanes and half spaces, that is vector x bar that satisfies Ax bar component wise inequality less than equal to B bar, Cx bar equals D bar. This region represents what we know as a polyhedron. This represents, that is an intersection of a finite number of hyperplanes and half spaces, basically represents a polyhedron. So, this can be just simply shown as follows. So, you can imagine having a large number, for instance, of half spaces, and for instance you can think of this as one half space corresponding to this, and you can think as this as another half space corresponding to this, and you can imagine the various half spaces. And now if you look at this region that lies in the intersection of all these half spaces, this intersection region of half spaces, in fact you can also throw a hyperplane into that intersection of half spaces plus hyperplanes. This is your polyhedron. Okay, so that is roughly, you can see, described by this region. That is described by this region. So, that basically forms your polyhedron. Okay. And for instance, you can take a simple example again. You can consider the polyhedron formed by these 4 pi hyperplanes, that is x1 greater than or equal to -1, x1 less than or equal to 1, again x2 greater than or equal to -1, x2 less than or equal to 1, and if you look at that region, that is something that everyone will immediately recognize. That is, if you take the 2 points -1 1 or x1 equal to -1, x2 equal to, so these are the 2 hyperplanes, these are x1 equals 1, so this is your x1, this is your x2, and this is x1 equals -1. So, this region is x1, and this is the region which is basically the strip, is the region that is x1 greater than or equal to -1 and x1 less than or equal to 1. And if you look at x2, this is the region pertaining to x2 equal to -1, and so this is the hyperplane for x2 equal to 1. So, this is the hyperplane x2 equal to 1, this is the hyperplane x2 equals -1, and if you look at this square region, now you can see the square which is formed by the intersection of these hyperplanes. This square is a polyhedron which is convex, that is the important thing. So, square is a polyhedron, and it's worth noting especially that polyhedron is important because it is convex. Now, in general, intersection of convex sets is convex, the hyperplanes and half spaces are convex sets, so their intersection is also convex. In particular, such a region is known as a polyhedron. okay, and it is very handy and it arises frequently in several applications. Okay. So, this square is a the square region is basically your polyhedron, okay, which is formed on the intersection of a finite number of half spaces and hyperplanes. Okay. To understand this better, we can start looking at an example which we might continue in the next module. So, let us look at an application of this concept of your polyhedron. And this will be in the context of cooperative wireless communication, that is, if you look, or cooperative base station transmission or base station cooperation. So, again once again looking at a wireless plus base station cooperation, also known as multi-point cooperative multi-point. So, base station cooperation, okay. And what happens in this scenario is you have several base stations. Typically in a wireless cellular network, what happens is conventionally a single base station transmits to a single mobile, but in some scenarios you can have several base stations cooperating to transmit to a single user or a group of users. And this is especially possible if the users are at the edge of the cell or in the region between multiple cells, where they can be simultaneously served by several base stations. Okay. So, each of these towers is, let us say, a base station, and you have a mobile that is being simultaneously served. In fact, you have several such mobiles, let us say, which are simultaneously being served by the. So, each mobile is being served, each user j. So, what we are saying is each mobile being served by multiple base stations I, that is, let us say we have k base stations, 1 less than equal to I less than or equal to k. Okay. So, we have base stations 1, 2 up to k, these are the base stations, base station 1, base station 2. So, k equals the number of base stations. Okay. And we have m total users, that is 1, 2 up to m, these are the number of users. These are the number of users. Now, what we will also have is we will have now remember, whenever you have a wireless transmission scenario, there is a channel between the transmitter and receiver, and this channel is fading channel because the wireless channel is fading in nature. So, that is characterized by a fading channel coefficient. So, you will have a fading channel coefficient Hij equals the fading coefficient, fading channel coefficient and Hij is the coefficient between the ith user. So, Hij channel between the ith, let us put it this way, between the ith This is the fading channel coefficient between the ith base station and the jth user. Okay, so this is the fading channel coefficient between ith base station comma, this is the fading channel coefficient, which means if you look at Hij is a fading channel coefficient, if you look at magnitude Hij square, this represents the power gain, or this represents what is conventionally known as simply as the gain. Simply this is also sometimes referred to simply as the gain. I mean, there can be an amplitude gain which is given by magnitude Hij. This is the power gain magnitude Hij square, which is the power gain, which means if magnitude Hij square is strong, then this received signal at the user j corresponding to the signal transmitted by base station I is going to be strong. But if this channel is in a deep fade, alright, which means there is a lot of interference in the channel, and as a result of this, if magnitude Hij square is very low, then the power received, alright, the received power by user j corresponding to the signal transmitted by base station I is going to be very low, and that can be attributed to the fading. Alright. So, this is the fading nature, this arises, this varying power level at each user corresponding to the signals transmitted by the base stations. This varying power level arises due to the fading nature of the wireless, or of a typical wireless channel. Alright. So, naturally what is the power that has to be transmitted by the various base stations so that each user receives the desired amount of power, or what is the power that has to be transmitted by the base stations corresponding to the power constraint at each base station. So, all these are various optimization problems, and these are things that we are going to look at during the course. My intention here is to formulate a basic problem related to this and demonstrate the applicability of the polyhedron, that is the convex set that we have just seen. Alright. So, we will stop here and continue this discussion, this practical application in the context of a cooperative wireless cooperative base station transmission in the next module. Thank you very much.